Hello and welcome to lecture 12. As you can see from the title, we're going to finish up our functional programming stuff and uncover something else called pattern matching. So we'll see what that is. So all week we've been talking about how to use functional programming, that is these operations on collections, to be more productive and do things in a more regimented, more testable, and more productive way to build a kind of our codes. And our generators often have collections of things, so having things that work in those collections are great. So we covered one-to-one operations on the first day. We talked about map and for each and zip, and then we talked about things like reduce and fold in the next lecture. Today, we're kind of covering a few remaining details, something called flat map, filter, and sum, but basically kind of rounding out the arsenal of things. But then we have a few other things covered today, right? We're covering pattern matching, which is to help make the code a little bit more clean, and you've been doing this not even knowing what it is. So once again, kind of peeling back more and more to language semantics and making it less boilerplate, more clear what's happening. We've shown option types in this course. Now that you know the functional programming constructs, we can see more ways to handle option. And actually, not listed, but time permitting, I will be also talking about the project if there's time. Okay, so let's fire up the old notebook. Good to go. So what is flat map? Um, well, map is great. And if you only know map, you're in good shape. However, some special cases where maybe flat map's even more powerful, right? So what does the difference? So map has this notion of one element in, one element out, one element in, one element out. Sometimes you're in a situation where the thing that is the element in quotes is actually a collection itself, right? So you're gonna have a collection of collections, and you're gonna want to do something with them. And so let's see how this plays out. I'm gonna comment some code out first. So let's say, for example, we have a range, and you may remember from before, seek.fill, right? We say, hey, I want, two threes. That's the way we syntax for it. I get two threes. Okay, now, given this range of 0 to 5, I'm going to call this code that's going to make a seek of that length. So what does it look like? You can see, oh yeah, I'm going to create empty because it's 0, as 0 zeros, 1 1, 2 twos, 3 threes, 4 fours, right? Trivial examples to kind of show what's going on, but already now we have a collection of collections, right? A vector of lists, but for today, we can handle it. Let's call them all seeks, right? Okay, so that's pretty cool. Now, maybe this is what you want. Maybe this is not what you want. Maybe you want these all to be in one collection altogether. We can do that. So going from a collection of collections and kind of removing that distinction into a single collection is doable with a dot flatten command. Um, Alternatively, and you see where the name flat map now comes from, I from the beginning am going to say, hey, you know what? Whatever this thing produces, concatenate this to the collection. Rather than making this an additional element collection, concatenate this to collection. So we're gonna get the exact same result as above, right? Here we did the operation and then called flatten. Flat map can, pull those together. Now, that's where the name comes from. To be fully honest, writing multiple large Scala projects and even chisel projects, flat map used in the situation, I use it, but it's not super common, right? That's not a very common thing. However, this next case is when we actually use it a lot more often. And that is, if you have this flat map capability, what you really have is the ability to say, I'm applying a map to something, and the output of that map is going to be collection. And I want the collection to be appended rather than treated as an element on its own. And so you have this notion of the output of map being a collection. A really useful application of this is actually now you have a map function that can return 0 or more elements, right? So rather than being 1 to 1, 1 to 1, maybe you want map times to not emit anything. So it's kind of like a map and a filter combined. Or maybe a situation where it's going to produce more things. And so let's say, for example, given L, I wanted to do a kind of filtering behavior where I want to only grab things that are even. Sure, it can do that, right? This is kind of another use of flat map that I think is more common. Um, in the grand scheme of things, you'd probably use map 5 times more than use flat map, but Doesn't mean flat map doesn't have its purpose, and you'll see a usage with the pattern matching at the end and the options where we find more value still out of flat maps. This is kind of why it exists. It's a very general, robust concept. However, there's different ways to kind of perceive it. And so I've shown you two ways of perceiving it. One is think of it as, calling dot flatten on map. Another is to think of it as just the output of your function is itself a collection, and we're concatenating and appending them together, right? And I think I have a picture for this. I do. So yeah, so here's map. It's called map on a collection. There's a outer collection and an inner collection. We, have one to one. Okay, great. These are collections. Now, if I was to do flat map, it combines all the elements together, right? If that outer level hierarchy is kind of intentionally evaporated. Cool. Questions so far? That's flat map. There's a few other handy functional constructs. So I kind of mentioned one in passing. Now let's make it more formal. Filter. And so in order to apply this, we need a condition. So this is called a predicate, which is a simple function which, given an element, returns a Boolean. And based on that Boolean, certain things happen, right? So as you can imagine, for a filter, you apply this function to every element. For every element that's true, we keep in the output collection. And for every element that's not true, we drop. We don't keep anymore. So, I could, as you see, I've defined this predicate. So function takes an element and, returns if it's, divisible by 2. So yeah, so going through, I have the range 0, 1, 2, 3, 4, 5. Apply is even. Of course, I get those. Now, what's interesting about filter, of course, in the Scala style, there's choices, right? So I could do filter. I could have a function to say I want to do not that function. Sure. Get the odd numbers. And you know what? Because Scala does this kind of stuff, rather than being filter and then having to manually negate your function, you can just say filter not. And now anytime a predicate is true, it drops them. Every time a predicate is false, it keeps the element. So yeah, that's cool. So this is very common in Scala, kind of have this notion of something you can definitely express, and then you can express it more concisely, more explicitly the other way. Um, as someone that came from the risk philosophy, sometimes seeing what is not strictly necessary functionality always makes you a little bit, nervous at times, but eventually it grows on you. You realize, oh wait, yes, if the thing really is a filter not, it's better to write filter not than filter and then manually negating it. Cool. Yes. Oh yeah, good question. So is this like before one of these scenarios? Absolutely. You can see I love the space style syntax, but L dot filter would be more clear what's going on. Um, my scheme background is showing. Yeah. So like I said, this is the kind of features that are built into Scala that makes it really easy to embed a new language inside of Scala. That's kind of some of these things, that choices they made. And yeah, I'm happy to embrace them. Okay, so what are things we do with these predicates? We talked about filter. That's pretty clear. There's actually these two ways of going across the entire collection. And it's actually interesting. You think about this. You may have written this code before, and this is nice. It's such a compact thing. So for all is, I'm going to apply this predicate to every element in the collection. And guess what? Its name applies. For all. In other words, it has to be true for each and every single element. If that's the case, the for all of that collection is true. If any one of them is false, it is going to complain. So, for example, if I say, um, are all the elements in that original range even? No, of course not. Now, if I was to sheet and then, paste this in there, so I only taking the even elements, and of course, yes, it's going to be true because they're all true. Um, and then there's also exist, which, as the name says right there, if only one or more predicate is true, then we get that result. So is there an even number in that range? Yes. Is that entire range all even? No. Right. So we have both for all and exists. And be surprised how you can start, using these things, using some surprisingly sophisticated code quite concisely. And I said these are robust patterns. It's not just some sort of hack. Like the mathematical semantics, what you're doing here is well understood, right? For all exists or terms from the math literature. Um, Defining a predicate. This is all very structured, right? Yes, yes, yeah. So exactly right. So I'm going to repeat this for recording. Yeah, this has some similarities we did before, what we did with the muxes in the prior lecture. Absolutely. So all these things, like I said, a lot of these functional programming constructs, they apply to collections, right? That's kind of the key point of them. Is we're given n things, how do we programmatically interact with that? For most of our lives, programming, we've been taught to do for loops, right? For loops and mutation. That's how we've done that stuff. And with these functional programming constructs, we can now interact with those n elements in perhaps a more structured way that doesn't necessarily require mutation, right? For all, you can imagine writing that by hand, right? For all, I'd probably have to say, let's do it right now. It's fun. Um, you know, uh, you know, all true. We'll say is false. Actually, you know what? Let's say it's true, and then we'll go through for x in L, and then we'll say all true equals all true and x. And then let's print. Actually, we'll just, yeah, then I'll just say all true and see what the result is. Oops. Oops, I didn't apply the predicate. We got to apply our own predicate. Okay. So yeah, so this thing did the right result. Instead of putting that in there, I applied this to the even elements, which better be true. Yeah, it checks out. Um, but yeah, you can see like this is a very nice, concise way of doing it. It's kind of way of these operations, right? Is that we have a collection of things, and the question is how do you want to interact with that collection? And yeah, as we talked about, there's some very common patterns, right? So, for loop iterating through something, that pattern is well captured by map, for each, fold left, etc. And you can see these different scenarios, right? The map is a one-to-one, we want the output. For each is one-to-one where we don't care about the output. Fold left, we're trying to combine those things down to one thing. You could almost imagine uh, writing for all and exist with fold left. You probably could. Uh, One thing I will point out is, like I said, remember map, the whole point is it's one-to-one. You shouldn't be trusting and have a certain evaluation order, right? If the evaluation order matters to you, that's you're kind of breaking the rules because map is one-to-one. They should all be parallel, right? And so if you the evaluation order matters, then there's some sort of secret side effects. Don't do that. No, it's not the hand. The reason why is, yeah, it's not going to be good. One thing I've not covered at all in this course is not relevant just to chisel programmers, but if you're a hardcore Scala programmer, you actually use these functional programming constructs correctly on your code. You flip the switch in the compiler, it's all parallel, right? That's amazing. Like, you're gonna rather be like, oh, I'm gonna go write parallel code. No, no, no. You just write your code with the functional programming constructs correctly, turn on the parallel collections, and boom, it's parallel. So that map has parallelism, right? You can imagine the map functions being parallel. It can do that. And so, yeah, embrace the functionalness. There's some niceness to it. This is kind of why it has some adoption. In certain places, you can do some things very gracefully and very cleanly. Cool. So, filter, right? Given and collect elements, things that are true, we keep. Things that are not true, we don't keep. Um, so let's put these together and build something up in concise code that's surprisingly concise for what it's doing. So let's say you are wanting to build a prime sieve. In other words, a piece of code that generates prime numbers. So I'm going to show you how just a handful of lines you can build up a pretty sophisticated one. So what do we do? Well, first of, we have this function I define, which is a multiple of, right? In other words, given two numbers, does A evenly divide B, right? Okay. Notice how I've broken up the arguments into two pieces, right? That should be like your hint, that, oh wait, it's probably going to partially apply this at some point. Yes, I'm going to partially apply this at some point. Um, so now let's see what we have. We have this function, for example, remove multiples of x. So, okay, given a collection of integers, given x, I'm going to filter and it's filter not. So in other words, whenever this is true, drop the element. And you can see how this kind of comes together, right? Okay, give a collection of numbers. Is it a multiple of x? Oh, if it's a multiple of x, we're doing filter not, drop it. So as the name implies, yes, we're going to remove all multiples of x. Cool. And then uh, what are we going to do? Well, um, we are going to go through some set of numbers, in this case, all numbers, let's say from 2 to 100. And we'll see some examples first. Before we actually do the final punchline, let's kind of build our way up. So, you know, that's all numbers being printed. Yeah, you can see that coming out. Let's actually print things out intentionally. How about all numbers that are not multiples of 5, right? Yeah, that checks out. I don't see 5 or 10 or 15 in here. So that's kind of that code working. So this is basically remove multiples of. So I can instead use that actual function we just wrote. Yeah, so we are dropping multiples of 5. This is a very famous prime step that's literally thousands of years old, which is basically how do I find prime numbers? Well, I start with a number, and okay, great. If it's empty, then sure, I'm done. If not, I say that number is prime, and then I remove all multiples of numbers from the remaining numbers, right? Um, and so these head and tail we haven't shown a whole bunch in this course, which I'm spending time talking about for a second. So given a seq, it's a collection of things. The head is the very first element. That's the dot, index 0 element. The tail is everything after the head, right? So it's 1 to the very end. And so basically what we're saying is, hey, given that collection, take the first element and keep it, and then call recursively on the remaining elements and remove all multiples of that element. In other words, I'm going to take 2 and then say 2 is in the collection. Good. Remove all multiples of 2. This pattern of having something that's like, the head and then appending on the rest, including the tail. This is a very common, pattern, not just in Scala, but in Scheme. And you see this a lot when you do recursion. This is tail recursive. There's nice properties with that. But more importantly, let's go ahead and see what happens. Yeah, you should recognize, oh yeah, here's the primes less than 100. And we did that in, 1, 2, 3, 4, like, I don't know, 7 lines of code, 6 lines of code. That's pretty cool, right? Um, so yeah, we were kind of applying these, predicates on predicates, filters on filters. But yeah, we filtered down the numbers from a 2 to 100 to only be the ones remaining are primes, right? We grabbed 2, dropped all multiples of 2. What's left? 3. Okay, great. 3 is a prime. Let's move multiples of 3. What's after that? 5, because 4 got moved when we remove all multiples of 2. So 5 is the prime. Remove all multiples of 5. What happened to 6? Removed by 2. What happened to 7? Oh, wait. It's a prime. Let's add it. So you can see that's kind of this sieve works. Cool. Okay. So here we are, going crazy with our functional programming. Um, we saw this earlier and kind of coming back to this concept. A lot of these common operations, like, adding, multiplying, uh, they just build these into the collection. So in other words, when you have a collection, you can call these operations and they're there. So you can say reduce and say plus. This is really clear, but it's also just a sum. You can do, reduce multiplication. That's the product. Min and max are there, and that's really helpful, right? You can imagine you're writing code. It's very productive and convenient to be able to say, hey, I want a min, I want a max. It's not just a matter of you saying, oh, me typing min is 3 characters. That's saving a lot of time compared to me writing out my own code to find a min. It actually helps the person reading the code, right? When they're reading your code, very quickly they understand what's happening, as opposed to reading your for loop or reading your fold left to find them in, right? So like I said, when these things exist, it's really good to use them. And yeah, we can go ahead and run it, sure. Um, cool. So, as I said, when these things exist, it's good to use them, right? Scala provides a zillion of these freaking methods, right? So how would you possibly learn them all? This is a problem that's not just in Scala, but any language. You can write code that works, it solves your problem. And if it solves your problem and works, you probably have no reason to doubt it, right? And so, given that, what can you do to make your code better, right? There may be features in language you may not be familiar with, maybe idioms in the language you're not familiar with. So, for example, let's say you're a longtime C programmer and you learn Python. In C, you're very used to, writing for int I equals 0, I less than n, I plus plus. Uh, you can do that in Python. If someone writes, for I in the range of 0 to n, that's correct code. But you're probably better off saying, for X and L and L being a collection, right? So kind of using that more direct iterator syntax is encouraged in Python. It's an idiom in Python. And so there's similar things with kind of learning that language's idioms helps your code be better. So how do you go about doing this? Number one, use an IDE, which I think most students are, right? But if you're using like a very basic text editor, please, please, please turn on Scala Metals to help you out a little bit. And it may tell you some of the things you're doing. You know what? Instead of this, you could do that. Take that suggestion in heart. It can help. Number two, code reviews, right? So we're going to talk about code reviews later on in this course. We're going to do some. Looking at other people's code, you learn when reading, and they also may tell you things when they read your code. So it goes both ways. That can help. The third, I'm going to give a shout out to this blog post, which I've been referencing for years. Someone took the time to write down in their experience common things people weren't aware of that were in Scala that are there. So uh, all sorts of things people will write in a language and maybe they didn't know Scala before, and now you can learn how to write more idiomatic code. And he kind of explains various things. Like, yeah, you know what? There is a non-empty, for example, right? And that kind of stuff. So cool. Worth doing. Make cleaner code. And if you forget, this link is, of course, also available on the course homepage if you want to take a look at that. Cool. Okay, so let's go super ham on this functional programming stuff and see what we can do. So let's say we have a matrix. Now, of course, there's going to be a library for this, linear algebra for this. This is not about the matrix. It's about just getting more practice with functional programming. Um, how's that going to look? Well, turns out the C command, you can actually give it multiple numbers rather than just one number, and you get a multi-dimensional collection, right? So let's go ahead and see that from the beginning. Yeah, I say, hey, give me a 4x4 of sequences, and then rather than having a static number, which I could do, I could just say make it all ones. Oops, I got to use the different braces for that. Oh, maybe I can't even do that. Okay, I got to use a function. Okay, we use a function. This is arbitrarily chosen just to generate the matrix. Okay, we have a matrix, 4x4. Let's say, for example, I want to use functional programming to grab a column. So what does a column look like? A column, I can easily, trace the pattern from my mouse, right? But technically, it's, going through multiple lists, right? So really what I want to do is I want to go through the outer collection, that's the first map, and then for each row, grab a row the thing that's third index, right? So if I want to get, column I, 0 indexed, this code will do that, right? So we're expecting, let's say column 1, that should be 1, 2, 3, 4, and whew, okay, that works. Now, what else do we need to do in order to do matrix multiplication? Okay, do matrix multiplication, many different ways of thinking about it. Maybe think about it as 3 nested for loops, or maybe think about it mathematically as, for every output element, there's a dot product of, a vector from one input, one row vector from one input, and the column vector from another input, right? So how do we do that dot product? Well, we're going to be given these two vectors, so to speak, so A and B, think of as two vectors. We can simply zip them together and then multiply them. So now we have all those pairwise products across those vectors, and then we can reduce them all to sum, right? So that checks out. Cool, that's dot product. So then if you want to be really aggressive, you might say, oh, could I do this with the placeholders? I think the answer is yes. Oh, we can't because it's a tuple. So no, we would be forced to, no, we cannot. That's why, because the zip created the tuple. It's actually not two arguments, it's a tuple, and that's why we had to do it that way. Sorry, yes, go ahead. Yes. So if, like we saw that before. If you have like a chisel component, you can definitely say underscore dot io dot in. That's totally fair. Yeah. Um, cool. Okay, we got a dot product method ready to go. So now let's put it all together, right? So in order to do matrix multiplication, i.e. mapmul, given two matrices, which for today are these sequences of sequences, we're going to go through A, and we say A dot map is going to do the outer collection first, right? So it's going to be basically going through A row wise. So we have a row of A. I'm trying to use names to help guide us along. Okay. And then for the length of that row, i.e. the number of columns, we're then going to map, right? So basically go through each column and basically we have a row of A, and then we're going to grab the right column we want for that column index from B, and then we're going to call our dot product method. So when this all comes together, this gives matrix multiplication, right? We're basically going to go through row by row, and for each element of each row, we're going to grab the corresponding column. Do the dot product. So we're going, left to right, top down, filling in this matrix. So you notice how I did matrix multiplication here. Nowhere on this slide is a var. Nowhere is a mutable collection, right? I've used functional programming to proactively, construct this all up. If you flip some switches in our compiler, it could use the parallel collections for some of these operations and use even multi-core parallel. Cool. Questions? Okay, let's see another way of doing it. So uh, here we did, map followed by basically map. This is one way of writing it. Maybe you find this following way more intuitive, right? Um, this is kind of like for every row, from A to A dot size, the outer collection. And then we're taking the first row of B to kind of get the number of columns. The prior slide kind of implicitly assumed that the number of columns would be the same, but here we're making that more, actually having more general, more flexible code is actually more correct, I would say. Actually, you know what? Before I forget, I might just change that. Because yeah, technically B could have their number of columns, and that'd be totally fair. Oh, but it's not row of B. We need, okay, now I remember why past self did this. This is always fun every year. Because you can see in the next slide why I did it that way. Because this is a mouthful. To kind of go in and grab the head in order to get the size. Sure. But yeah, same corporation, still two maps. Maybe that formatting makes it more clear. What's absolutely wild is here you notice how we're kind of building up this collection. We're going, row by row, element by element in those rows. If we use that tabulate method from earlier and say, hey, I want to do a tabulate where for every given element ij, it's going to be the dot product of a row of A and a column of B. And we shouldn't have two definitions of mapmul. It also works. So yeah, I mean, not shown on this slide are dot product and grab call, but in a surprisingly few number of lines, we've written matrix multiplication where the actual core logic is now like one line, which is kind of wild, right? So it's a dot product, and we get this ij from tabulate, which is kind of iterating through this space for us because guess what? It's a very common pattern. If I have a multi-dimensional collection, I'll probably use nested for to kind of iterate through it. Why not encapsulate that pattern into dot tabulate? And they did. So that's kind of convenient. For you, in many assignments, you're probably just going to do um, dot tabulate on a 1D collection, but you can do it on multiple collections. For those of you doing homework 3 still, you've probably been playing with this kind of stuff a game of life right now. And so seeing both with for loops and functional programming. Cool. Questions? Okay. Now, the as promised pattern matching. So what the name implies is a way to make the code recognize things and kind of connect it up together. So we're all very familiar with programming and doing things like equals equals to do comparisons. And we can do if else. And we've also seen things like switch. Switch is a chisel construct. Um, Match is a Scala construct that does pattern matching. And what I'm showing even just in this one slide is more than just a switch statement, right? Yeah, you can have very clear cases where, yeah, a single number is handled a certain way. You can have situations where you have an or, right? Or you want one or three to have this behavior. You can do that. You can even apply a little if statement. You can, name the variable and then do something with that variable. That's fair. Um, and there's even a default case, which is the underscore. So for example, yeah, you can see it kind of goes through these cases. Okay, if it's 0, it matches 0. If it's 1, it goes there. If it's 2, it's going to be even because satisfies this. 3 is still, nah, that's not what we're looking for. 4 is even. And then 5, found it. And then anything bigger than that, oops, that's a new one. Oh, that's why. Somehow I managed to comment out code. I've never seen that before. Oh, whoa, it changed it to a not code cell. That's wild. Okay. Well, here we are. It's working again, so we're not going to mess with it. But anything that doesn't match any set of criteria, like even -1, for example, is going to be utter, because that's matching this default case. If it matches none of these, there's a default case. If I don't have a default case, it's actually totally fine. It's just going to work until it doesn't have a default case and it tells you there's a match here. There's nothing to match with. Um, cool. Questions? So this is doing it on like, a numeric type, right? Where the pattern matching is really powerful is using it for other things. So let's use case class, which I've already been hyping up earlier in the quarter. Um, so we're going to pattern match on case classes. So for fun, let's have vehicles. So we'll have a helicopter and a submarine. They both have a color and a driver, sure. And they have a collection that has both helicopters and submarines in there, right? You see which vehicle type it is, the color, and who's piloting it, right? Um, so first off, I can simply just go through these that collection and just match. Helicopters in one case and submarines in another case. It's a very common thing you can do where you have these subtle nuances of types, and you can just match on the types. So yeah, I can go through and print out. Oh yeah, hey, I saw a gray helicopter, a blue helicopter, a yellow submarine. Sure. Now where it gets really kind of amazing to me is where you can play with this and say, all right, I want to go match, but rather than just matching the type, I want to have some of these fields in the type be set, other ones be unset. So for example, this is telling it, hey, match anything that's specifically a helicopter and specifically blue, but the driver can be anything. Now you have that variable for the driver, and you can say it has a blue helicopter, for example. Or if given a submarine and the color is not yellow, I'm going to print out, so and so submarine, right? So you can see these kind of examples play out. And so, we had only a blue helicopter match these rules because the other one's the gray helicopter, so it's helicopter, but the color doesn't match. The submarine is a yellow submarine, and we were looking for a not yellow submarine, so we lost that one. This is pretty cool. So you can do some pretty cool stuff with this. Um, for research, I've built a project that looks kind of like a compiler internally, and so yeah, you can imagine going through the interpretation of a language, an IR, and you can match on different node types for certain conditions really powerfully. This is just unimaginably productive for that kind of work. Um, Pattern matching is pretty awesome. Cool. So the key to pattern matching is being used in language is case. We saw that in lectures even today, I think, where we've had so many things with tuples, like right here. This technically is pattern matching, right? The thing it's pattern matching against is on one side is the tuple, on the other side it's these two variables, and it's kind of making that connection by saying, hey, try to pattern match these two together. So that's the same, power in that language. Cool. So then moving on, how are we doing time? Oh, we're doing perfect on time. We talked about more graceful ways to deal with option. So remember, option was something that's in the language where it either has a value or there's not only not a value, we know by in the type there's not a value. So either it's none or it's something that actually has, a value. And beyond it being helpful just in Scala in general, in Chisel we found this helpful for things like having an optional I/O port, right? We want to have a port that's either there or not there in the final hardware. And so if you have a sum type in the bundle, that turns into hardware. If it's a none type, it's pruned. So you can have this kind of very nice description. So let's say, for example, we want to generate some data. Let's say L is going to, be the numbers counting up from 0 through 4. And hey, if they're odd, we'll go ahead and say they're some. If they're even, we'll make them none. So maybe it helps if I was to print out L. Actually, no, you can see that down here. Right, so see L, for even 0 to 4 is none. For the odds, 1 and 3, it's there. Cool. Um, Now, when we taught you a few weeks ago, when working with an option type, we said, okay, well, you don't know if it's actually there, so you got to see, is it defined? And if it is defined, meaning it's not none, you can go ahead and say dot get. And so, as you can see going through it, yes, the ones that are some are 1 and 3. Let's say you were impatient and you didn't check. You're going to call dot get on a none. That's an exception, right? You can't get something that's a none. Okay, so what are the alternatives to this? It makes this a little bit less verbose. It makes this option type seem even nicer. One is something called get or else, which is, hey, uh, you know, as the name implies, either give me something or give me this default value. So either whatever that value is, I'm going to get, because index one is one, one is something. So yeah, you get that value. Otherwise, I get negative one. If I say give me the next one, which is a none, it's going to give me negative one. So it's get or else. Okay, that makes sense. Now these following ones are showing you why we covered this concept today. So given a collection where of some nuns and some sums, okay, what if the ambiguity now is going to be removed? What if we don't care about distinction anymore? We just want the real data. Well, guess what? Dot flatten is going to drop the nuns. It's also going to remove the sum wrappers around the thing, right? So this was an option type inside there. Now it's just the result type. So that's pretty cool. So wait, so I called dot flatten, and it's there. Um, and so you may see people, for example, in code, uh, do this, right? Oops. Oops, I never mind. That's why you can't do that. Okay. But people use flat map all the time on option types in order to kind of get the right behavior. Um, okay, so then flatten's cool. You can also pattern match, right? Yes. So flatten in this case, given L, which is all of this. So L is the collection of options that inside the options int. And you see it includes, none or an actual value as both. When I called out flatten, it removes all the nuns and it removes the wrappers around the sum. So it went from option of int to int. So yeah, so that distinction's gone. Okay, and then the pattern matching, right? So uh, for the pattern matching, we're just going to iterate through it. I'm using for each because it's iterating through, and I don't care about the output. And you can see using the option types is really handy. I can say, hey, if it's something, give me that something, right? I want to print it. If it's none, I will just write out it's, was empty. And so there you go. That's pretty cool. So we can kind of work in this a different way. And then also, for each is smart enough to, you see the output didn't change. If you give it an option type to for each, it will do it if it's there and not there if it's not there, it won't do it. So if I say, well, one, we know ones exist, it prints that one. But the zero we know is a none, it doesn't do that. So you use someone's code, occasionally you might see someone write code where it's like, why did they call, for each on a one element thing? It's because they're removing the options. So occasionally people have a lot of code with a lot of options. These are the various ways you can interact with it. And it's kind of at first maybe a little daunting, but over time it gets more graceful. Um, There's also the kind of thing an ID can really help you see, right? If you have an ID and you can kind of hover over things, see what it types, and see things kind of percolating through, you recognize, oh, one point is an option. At some point later on, to actually do real work, it needs to be non-option. You can kind of see that transformation happening. Cool. Questions? Yes. The most common chisel application is the one I described, where you have options to have we call them optional IOs, right? In other words, ports we're not always going to have in a hardware design. In Scala, it's a really common thing to have options because you know you may have some parameters where you want to indicate this parameter is not active, right? And you could have the parameter field and another field floating around if it's just like a boolean saying, oh, is this active or not? Or you can just make it an option and it kind of combines the two together. Um, so it's helpful in the Scala set. You can kind of write arbitrarily complex or uninteresting Scala, but for chisel direct application, yeah, usually it's for optional IO. Okay, well, we have 8 minutes. I'm going to try and give the project overview and see how that goes. Hopefully, people will watch this online and catch up. So, as you're well aware, this course is a project. We've been churning through these lectures. You've been zooming by, right? Before you realize that you've been learning quite a bit of Chisel, quite a bit of Scala, writing a lot of code. It's worth to shift gears. As you kind of go more into project mode, now that you have these tools, you're going to go ahead and use them to build a project. And I think the project is kind of the whole point of this course, right? To really build a generator, and you're going to develop it, revise it, extend it, etc. So um, I encourage pairs. The course is small enough this year. I'm not going to mandate it. Some years the course is big enough headcount wise. I'm saying like you must work in pairs, otherwise no, I highly recommend the pairs. I think you learn a lot more. You can build something really cool together. You can build something bigger, of course. The expectations for the project scale based on the number of people in the group. So, um, you work alone. Yeah, you're expected to do less than a pair, but you're expected to do more than half the size, right? Because there's not a 2x gain from a pair. Um, so, what should you do? You're going to be building a generator. So, you're not just going to do this out of thin air. This is a process, right? So, in the process, you're going to kind of propose it, you're going to get feedback, you're going to develop it, keep iterating, extending it, doing all that good stuff, right? And so, what are kind of key things to be aware of? You're going to pitch a project. It's going to be unique to you and your partner. Everyone's going to do different projects throughout the course. You're going to get feedback, you're going to develop it. At the end, you're going to present to the class and all that goodness. In terms of how to think of what's the reasonable size, uh, think of like 2x the most recent homeworks. I say most recent homeworks, think of like, especially like next week, right? Or like something even longer. And so like that's a better way to figure the complexity. I keep moving the slide back in the lecture sequence. That's why maybe it's not as clear. So maybe I'll tweak that wording so it's more clear for the future. But always good to talk to the staff, and the staff in this case is me this year, about what you're thinking about. And you can kind of give some early feedback. And so even though it may not sound like that big of a project, it's bigger than you realize because unlike the homeworks where I give you scaffolding of existing code, I also give you documentation explaining exactly what to do. You're figuring out what to do. So that process of figuring out what even needs to be done, that takes time. You're starting literally from scratch. There's something called the project template repo. So you clone that repo, or you say you fork that repo, and that way you get all the chisel SPT stuff there all populated for you. But other than that, it's blank, right? It's up to you to kind of make this. So that telling this conversation now, even a few weeks to the deadlines for the project, just to kind of talk to neighbors, build project pairs, get that going. Um, so what does the timeline look like? Uh, so technically we're in week 4 right now. So I said we're a little bit earlier this year. But in the next 2 weeks, find a partner, talk things over, come to office hours. We want to get feedback from the staff. If you can't make office hours, feel free to send me an email and I can try and give feedback via email. Um, get the ideas going, get the groups going, get the ideas going. Then you're going to write a proposal. It's a one pager. And from that one pager, I'm going to give you feedback in person during class time. So this is one of the few times in this course where people are going to be required to come in person. And so really the only times in this course your in-person is required is during the project proposal discussion for your project course to make that valuable, as well as at the end of the quarter for the final presentations. Otherwise, yeah, I appreciate it as we come, but it's technically not required for your grade. Um, but for the proposal feedback, yeah, you need to be here. For those of you taking the undergraduate capstone course. I'm talking to Professor Harrison. So yeah, we've scheduled it such that you will not be required to be in person in the same place at the same time, two courses. So um, yeah, the shift currently is it'll be Tuesday here and Thursday in that class if you're not both. So if you're in both classes, you're going to be put into the Tuesday pool. But anyways, you know, build a project, get the loop going early, keep adding on to it, keep improving it. Uh, some intermediate deadlines see next slide, and then finally you're going to finish it up, present it, call it done. Cool. So what that should look like, like I said, the first thing is going to be having a proposal, which is one page. There's going to be instructions posted on the page explaining what I want to see in that proposal, but for now, think about basically what is the generator trying to do, what's it supposed to do, what's it look like when it's done, and then given that vision of the final product, think a little bit about how you would get there, right? How are you going to get started? What's going to be the simplest thing you get running first? And how do you kind of build features onto that? And we're going to use the lectures time, like I said, to get feedback on proposals. Um, Along the way, it's kind of various intermediate deadlines. For example, at one point, we're going to ask you to a link to repo that works. It's not going to be complete, but we need to be able to clone your repo, run some commands, and see some things happening, right? And so I said we want to see, you know, not just, you know, some chisel code, but chisel code actually talks to a test bench and actually runs something in simulation, produces Verilog, et cetera, right? So we actually kind of want to see that integration early, even though it's not feature complete yet, to kind of get things going. Then there's going to be time period where you're going to be, for example, you're going to give your project to another group, and they're going to give their project to you, and you're going to give each other feedback on via code review. So seeing other people's code, you're going to learn things, getting feedback, you can try to make that more clear. So there'll be a code review process. Then the final week, of course, we'll have presentations. And then following the presentations, I'll be emailing you feedback. And from that feedback, you have an opportunity to revise both your project and your presentation before it's like fully graded. So there's going to be a grade based on presentation, but there's a chance to revise and then improve the overall grade. Um, Now, the last little step is that uh, for the sense of coursework, you are required to present to your classmates, but otherwise, there's nothing public about what you're doing. And to be clear, even though I'm on YouTube all quarter, presentations are not going on YouTube, so you're not going to be on that part of the internet. Um, but I encourage students to make their repos public, right? These are on GitHub and just make it public. And so far, that's what everybody does. And so, not a requirement, but it's encouraged, and people do it. And that's great. And so you can see if you go to the homepage, you can see prior groups projects are all public. You can kind of see what's there, get some inspiration. Um, I picked some dates to get the ball rolling. I reserve the right to fine tune the schedule. For example, as I'm, you know, negotiating with guest speakers, making sure be compatible with their schedules. They're very grateful for their presence. I may need to move some dates around a little bit, but this is the first order we're looking at. Um, cool. One thing which I didn't even mention at all, I should mention some, is what are example projects, right? Anything that has some amount of generation and parameterization is what we want for this course. So if it's a single static function, that's not as exciting as those parameters doing some sort of generator. So we've had students do things like, hey, let's do this compression protocol for LTE. Let's do the math behind GPS. We've had students do things that are totally fun and not real hardware. Like, I know someone does a Mandelbrot fractal generator, and they did that as a chisel thing. It was kind of cool. Or like, given a grid size, you can compute the fractal, and that was kind of neat. Where people do things like Snake. I think one of the most dramatic presentations we've seen in this course was somebody built a generator that could take in either Super NES or Game Boy ROMs and play the music from them. And it could actually do that. And they implemented that not just in Chisel, but also got to work on FPGA. And then for bonus points for fun, they found a system Verilog online to drive the HDMI port in FPGA and actually gave a presentation from the FPGA. So that was like the most extreme presentation of all time. Not required to get made in the course, but that's an example of how far you can have it go if you want to have fun. But yeah, this kind of thing to think about. Talk with a partner, find a partner, talk it over, talk to your staff about it. If you have absolutely zero idea what project to do, I can suggest some. But usually I think it's best if students have some interest. And yeah, it's the most interesting one when somebody has a little bit of parameterization, a little bit of generation ability to it, rather than being, you know, a very fixed function thing, a little bit more knobs to it. Cool. Questions on that? It'll be an ongoing conversation, but that's good for starting. Okay, well, that's it. Have a good weekend, folks.